talk about prime numbers again, but this time we will talk about what are called gaps between primes. So, we know there are infinitely many primes and we can write all of them down. It's 11, then there is 13, 17, 19. And if you sort of try to write this down up to 100, for example, all the different prime numbers, you will see that they are often to be found. Once you find one prime number, the next one is not too far from it. So, here initially the gaps from 3 to 5, the gap is a 2. So, that is what this word gap here means, the differences between successive primes. So, the gap is a 2, it is a 2 again, 4, 2, 4, 2 and so on. It's often just 2s and 4s, maybe sometimes 6s. But as you sort of go down the list, you will find you will reach at some point 89 and the prime after that is actually 97. So, this gap here is for the first time a gap of 8, this series. And the other example that we looked at was 113 and the prime after that, as we found, was 127. So, this gap here is actually 14, right. So, these gaps are rather irregular. So, it's very hard to say what the gaps look like, how they change, how they vary and so on. There is no nice pattern that one can write down explicitly, but what we would like to know and what we will consider today is whether these gaps can be very, very large, as large as we want, okay. And this is the statement we'll try and prove. It's an interesting fact, maybe not so surprising if you sort of write down prime numbers, if you try to write down prime numbers maybe up to 1000 and so on. So, you will see that every now and then you see these very large gaps between two successive primes. So, let us make a precise statement. So, the informal statement that we want to make is that gaps can become very large, as large as we want. So, if you want to find two prime numbers which differ by more than 100, you will be able to do that, okay, two successive primes. So, here is the precise statement: given any gap or any natural number n, there exist successive prime numbers p and q. So, let me assume that p is the smaller of the two. I can find two successive prime numbers p and q with p less than q such that their difference, which is the gap, is greater than this number n that we chose. Okay, what this means is, if you, like I said, if you take n to be 100, then you can find two successive primes whose difference is 100 or more than 100. Well, here the way I wrote it is greater than n, or let us say greater than or equal to n. I can find two primes whose difference is 100 or more. Okay, so here's the idea of the proof. Again, let's sort of think about it in terms of the number line. So, if you draw the number line and you mark all the primes on it, 2, 3, 5, 7, etc. So, as you keep going, so what we are saying is that somewhere we should be able to find p and q such that the difference between them is greater than or equal to n. Now, what does that tell you about the numbers in the middle? What do we know about all of these numbers? Well, p and q are successive primes, which means there are no primes in between them. So, these are all composite numbers. So, what this is saying is that I can find arbitrarily long sequences of composite numbers. Okay. So, if I write out the integers, I can find long sequences of composite numbers inside them. So, that is the idea of the proof. we will try and find such sequences. And this is a very nice trick. We'll find such sequences of composite numbers, and to do that we will use this thing which comes up again and again in various places, including in counting, binomial theorem and so on, the factorial. Okay, so what is a factorial? Remember, this is the product of all the numbers till n. Okay, now if you look at the numbers n factorial plus, so I am going to try and make composite numbers using n factorial. So here is the first one, look at n factorial plus 2, here is another one, n factorial plus 3 and so on. I want to go down all the way till n factorial plus n. Okay, and in the middle I will have say n factorial plus k, where k is any number between 2 and n. So let us look at each of these and see that they are all in fact composite numbers. Okay, so let us calculate. To say this is composite, what you have to do is to show that you can find factors, right? You should be able to somehow factorize it. Now observe that this number n factorial plus 2 and the number the number 2 and the number n factorial have a common factor of 2. So we pull that common factor out. So it is 2 times. Now I write the remaining numbers 3 into 4, 1 into 3 into 4 till n, and from 2 I pulled out a 1. So I found 2 factors, one of them is a 2, the other is this product. Likewise, the number n factorial plus 3, the 3 and the n factorial have a common factor of 3. So I will pull that out, think of it as 3 times 1, 2 and then 4, 5, 6 till n plus 1. Now we keep doing the same thing. If k is a number between 1 and n, this is just the product of all numbers till k minus 1 and k plus 1. So I have omitted k here plus 1, and the last guy is just n, and this is in fact n minus 1 factorial now, product of the remaining numbers. So what we have done is to show that every one of these numbers we constructed is composite by explicitly writing out some factors. Okay, now observe these are all consecutive numbers, right? N factorial plus 2, 3, 4 blah 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 till n. So how many such numbers are there? So we have concluded therefore that is a consecutive sequence, I should say it's a sequence of consecutive composite numbers. Now what is the length of this sequence? How many numbers does this sequence contain? Well, it contains n minus 1 numbers. So this contains n minus 1 numbers. Okay, so now we are more or less done, because now we go back to our number line. So we go back to the number line, and what we have found is this sequence of n minus 1 consecutive composites, right? So these are all composite numbers, there are n minus 1 of them. Now what we do is we look for the prime numbers which occur to the left and to the right of this string of numbers. So there is some prime number, look at the very next prime number which occurs after this. So look at n factorial plus n, and let q denote the smallest prime number bigger than n factorial plus n. Now look at the other end, which is n factorial plus 2, and let p be the largest prime number which is less than n factorial plus 2, right. So I take the nearest primes on both sides to this string of composites, and now observe, so let this be prime, and now observe that q minus p is at least n, right, because there are n minus 1 composites in the middle, and in fact it is at least n plus 1, because we sort of have to at least go one step on either side. Okay. So to write this out formally, this is the smallest prime number that is bigger than n factorial plus n. take that to be q, and take p to be the largest prime that is smaller than n factorial plus 2. So that's the end of the proof. Okay. So gaps between prime numbers can get extremely large. Now notice one fact here, we are not saying that the gap is exactly n. So if you give me n, I am not saying, say if you give me 100, I am not saying I can find for you a pair of prime numbers, successive prime numbers whose difference is exactly 100. Okay. So that is a much harder statement to try and make, but all we are saying here is that you can find two successive primes whose difference is 100 or more. Okay. And if you actually work this out in examples, often you will produce something that is much longer than n, the gap.